Okay, we're on lesson 12, and the title is Angles Associated with Parallel Lines. So in this lesson, we're going to look at what happens when you have a couple parallel lines. And the picture you're looking at right now, line 1 and line 2 are not parallel, but we want to look at what happens when they are. So in a minute we'll get there. But this lesson is really cool and I'm excited about it because we're going to use what we know about basic rigid motions to do some informal proofs about the measures of these angles. And so you're going to actually put to use what you've been learning in the first 11 lessons. So it's pretty cool. Now you may have studied this topic before and you know a lot about these angles that are formed when this line crosses a set of parallel lines, but you have probably not done proofs of those to the extent that we will in this lesson. So I encourage you to keep an open mind and and work with me here. So you're going to need a protractor for this first part, Exploratory Challenge 1. If you don't know how to use a protractor, I've added a Khan Academy video on using a protractor to this playlist. And feel free to go look at that because a lot of times students are kind of shaky on how to use the protractor and how to line it up. But so you're going to take a few minutes and just measure angles 1, 2, 3, 4, 5, 6, 7, and 8. And you can record it right on your paper as you do it. So, for instance, I would come up here to angle 1. I can line up my protractor right here at the vertex. And then I want to get this right on 0. For this one, this angle is opening this way. So I'm going to use the scale out here. Sometimes it's going to be useful to you to extend these lines a little bit, which is perfectly fine to do because it doesn't change the measure of that angle at all, but it helps me read my protractor. So I can put it right here, line it up. It's easy to get a little bit off. If you get a little bit off on the vertex or a little bit off on the line, it can throw off your measurement. So I can see this is 110, there's 115, 116, 117. So I could say this angle 1 here is 117 degrees. Okay, so I'd like you to do the rest of the angles in the same way. Come back and we'll check it together. Okay, I'm just going to go ahead and fill in the other measurements you should have gotten. This one, 63 degrees. This one, 117 again. And this one, 63. And then down below, we've got angle 5 at 104 degrees, angle 6, 76, angle 7, 104, and angle 8 is 76 degrees. Okay, so we've got these angle measures. If you're off by 1 or 2, down here it's okay. But notice that these angles that are on a straight line here are adding up to a full 180 degrees. So 104 plus 76 is 180. So you can check your measurements that way. You should have gotten something similar to this. So the directions here asked us to notice which, if any, angles are equal. So we can write that over here. Notice that the measure of angle 1 is equal to the measure of angle 3. And the measure of angle 2 is equal to the measure of angle 4. And then down below, I have the measure of angle 5 is equal to the measure of angle 7. And then the same thing for 6 and 8. Measure of angle 6 equals the measure of angle 8. And if you remember in an earlier lesson, we already looked at this and we saw that these angles had a special name. These are all called vertical angles, and they form when two lines cross. Okay, and vertical angles are always congruent, are always equal in measure to one another. And the reason for that, and this is, you know, anytime we're explaining why, we're giving an informal argument. In high school geometry, you will be giving formal arguments. You have to clean it up a little bit, but we can give an informal argument, and it's this. I'm gonna trace out these two lines here, and I'm even gonna, let's do it this way. Let's put on our paper, we can label a couple points. Let's label A and B right here. And I can mark those because I'm going to do a rotation, right? I can do a rotation of okay, I wanted to label one on this. I don't need another point there, but I'll label a point here on this line. See, because I'm going to rotate this line 180 degrees, and I want to make sure I've got it matched up. So here's my point C. Here's my point A. And if I rotate, and here's my angle 4. If I rotate 180 degrees, point C is going to be collinear, and I'm rotating around that intersection point. It's going to end up on the line up here because C, the point of rotation, and C prime will all be collinear. We saw that in an earlier lesson too. So notice that, and then the same thing with this point here, A and A prime will be collinear with the point center of origin. So you can see that angle 4 maps with 180 degree rotation to angle 6. And we could do that for any of these vertical angles. So we found, what we did is we found a basic rigid motion that mapped one onto the other, and we could prove that they are congruent that way. All right, so in geometry, you're also going to find it useful to look at other pairs of angles when these lines cross. So I've got line L1, L2, and then this is called our transversal here. So there are angles that are called corresponding angles, and you can take notes on this now, and it's also in your lesson summary. Corresponding angles are angles that are in the same position where the line crosses. So for instance, if I have this, I have line M crossing L1 and L2. So some corresponding angles would be angle 5 and angle 1 because they're both right above the line on the same side of the transversal. So corresponding angles would be angle 1 and angle 5. Some other corresponding angles would be angle 4 and angle 8 for the same reason. They're both right below the line that forms the angle and on the same side of the transversal. So angle 4 and angle 8 are also corresponding angles. See if you can find a couple more pairs of corresponding angles. And pause it if you want to. But angle 2 and angle 6 would also be corresponding because they're in corresponding positions again. And then the last set would be angle 3 and angle 7. Okay, so those are our sets of corresponding angles. I'm going to run out of room on this paper, but we're going to try. Okay, so the other type of angle we have are called alternate interior angles. Interior angles. Okay, and those would be ones that are on the inside of our two parallel lines. So they're in between here, but they're on alternate sides of the transversal. So an alternate interior angle would be angle 4 and angle 6. Okay, so again, they're interior because they're inside the two lines that we're talking about. And they're alternate because they're on alternate sides of the transversal. So our other pair of alternate interior angles would be 3 and 5 because they're on opposite sides of the transversal. Okay, so then we also have alternate, and I'm going to come just up just a little bit. I have alternate exterior angles. Okay, so these are exterior because they're on the outside of our two lines that we're talking about. Okay, so they'll be on the outside here, and they're alternate because they're on either side of the transversal. So we've got angle 1 and angle 7 would be alternate exterior angles. And can you find the other pair? Okay, it would be angle 2 and angle 8. So angle 2 and angle 8. So if you've not had this vocabulary before, you're going to want to know what we're talking about when we talk about vertical angles, corresponding angles, alternate interior, and alternate exterior. And you should be able to find those on your diagram. Okay, in this next exploratory challenge, we have a similar diagram with two lines cut by a transversal, M. But in this case, notice that lines L1 and L2 are parallel. Okay, so we're going to do the same thing we did in the first exercise where we measured all the angles. We're going to measure them again. So get out your protractor. You can pause the video and go ahead and measure the angles, and then we'll check them together. Okay, so you should have gotten something pretty similar to this. Angle 2 is 141 degrees. Angle 1 is 39 degrees. Angle 3 is 39 degrees, as we would expect, because they're vertical angles, and angle 4 is 141 degrees. The thing that's happening now is that angle 6 is also 141 degrees. Angle 5 is 39 degrees. Angle 7 and angle 8 is 141 degrees. So, so we got the same result of the vertical angles being equal in measure in both cases, but now we have these other pairs of angles that are also congruent to one another. So we want to explore that. So now we want to work through questions A, B, and C below this diagram here. And let's look at question A first. And I'd really like you to pause the video and not just listen to my explanation. It's really much more, you're going to understand it much better if you try it yourself first. So let's read part A. What do you notice about the measures of angle 1 and angle 5? Well, we already said that we noticed that the measures of angle 1 and 5 are equal. And we want to know why this is so. So why do you think this is so? And once again, when you answer questions of this sort, why do you think this is so, what you're doing is making an informal proof. And so it says to use your transparency if needed. So think about what we're going to be doing here. We've been using these basic rigid motions. So what kind of basic rigid motion could you use to prove that these two angles are of the same measure? Apart from using our protractor, of course. So go ahead and pause the video now and think about that. Okay, so angles 1 and 5 are what type of angles? Well, they are in the same position. They're both right above the line on the same side of the transversal, so they're corresponding angles. Angle 1 and angle 5 are corresponding angles. And you may have noticed that if I trace out angle 1 with my overhead, and I'm actually going to do something on my diagram here. I'm going to label a couple points. I'm going to label point A and point B. And the reason for that is I want to define a vector AB, because hopefully you noticed that I have a translation here along vector AB that will map angle 1 onto angle 5. Okay, so that's great, but how do I know that these lines match up? Well, I know I'm moving right along the vector, so this line here is all part of the same line. But what about these two? Going from this position on L1 to this position on L2. Well, because I know that when I use a translation, parallel lines are mapped to parallel lines. And so since I'm told that L1 and L2 are parallel, I know that once I get here, that these angles have to be the same. Okay? Whereas notice if I go back to this diagram here, and I try to do the same thing with the corresponding angles, they don't map. And here's why. So here's a pair of corresponding angles on this diagram, angle 2 and angle 6, and if I define this vector here and I slide it down, notice that these angles don't map because this line here stays parallel to that under the translation. And I've been told that L1 and L2 are not parallel in this diagram. Therefore, those angles are not congruent, not the same measure. Okay. So I'm using what I know about parallel lines to make these informal proofs. So what could we say here then? What could we say in our explanation? And hopefully you will try to write this on your own first, and then write it. What did you notice? Well, we noticed that the measure of angle 1 is equal to the measure of angle 5. Why do we think this is so? We think this is so because if I translate angle 1 along vector AB, then angle 1 maps onto angle 5. And translations preserve, I could say more. I could say translations preserve angles, measures of angles, degrees, however you want to say that, degrees of angles. Okay, therefore, measure of angle 1 is going to equal the measure of angle 2. But remember, it's because these lines are parallel. Because these lines are parallel, when I translated, a parallel line maps to a parallel line, and therefore those angles are the same measure. Okay, so what I'd like you to do now is look at B, and in B we're looking at angles 3 and angle 7. What do you notice about their measures? Well, 3 and 7. The measure of angle 3 is equal to the measure of angle 7. Why do you think this is so? Okay, so use your transparency if needed. And are there any other pairs of angles with this same relationship? If so, list them. Okay, so you're going to pause the video now and do that with your transparency and listing all those pairs of angles, and then come back and we'll talk about it together. All right, so the measure of angle 3 is equal to the measure of angle 7 for the exact same reason that the measure of angle 1 was equal to the measure of angle 5. So let's just do it one more time. I'm going to draw line L1. I'm going to trace the whole thing here now. And we're going to again translate on vector AB. Translate along that vector, because that's going to map line L1 to line L2 because they are parallel. Let's mark our angle in case we forget which one it is. This is angle 3. And we're going to show that it maps through this translation, maps onto angle 7. So let's go translate along that vector right here. And because L1 and L2 are parallel, I know that those are going to match up. This line is going to coincide. The translation of L1 is equal to L2. And this line here is along line M. It coincides as well. So these angles will have to be the same because the angle is preserved and maps directly onto the other one. So angle 3 is equal to angle 7. Okay, so did you find, so I wrote out the reason again. It's the exact same reason that 1 and 5 map onto each other. So the other pairs of corresponding angles that we could prove with the same logic are the same would be 4 and 8. So we're asked to list the others. So we've got angle 4 and angle 8, and then angle 2 and angle 6. So here's 2 and 6 that we could, 2 and 6 that we could prove by translation along vector AB that they would be equal in measure or congruent angles. All right, because degrees of angles are preserved. Okay, so now we're going to look at exercise C here and explore angle 4 and angle 6. And this one, we notice that they're congruent. The measure of angle 4 is equal to the measure of angle 6. Let's write that down. The measure of angle 4 is equal to the measure of angle 6. But why do we think this is so? Use your transparency if needed, and then list other pairs that would have the same relationship. All right, so this isn't going to be the same rigid motion, is it? Because we can't just use a translation in this case. So let's look at it. If we've got angle 4 right here, you know, we can't just translate it over here to angle 6. So we're going to have a different rigid motion that we use. So I'd like you to really use your brain and come up with something. There are a couple different ways to do this. One that uses a single rigid motion and one that uses 2. So see if you can come up with one or both of those. So pause the video and then come back and we'll do that together. Okay, so in part C, you were exploring angle 4 and angle 6. So are these corresponding angles? What are these? If you go back to your notes here, and of course this diagram is, no, it's labeled the same. If you go back here, the corresponding angles are the ones that are in the same position, you know, in relationship to these two lines and the transversal, so 1 and 5. But 4 and 6 are not. So 4 and 6 fall under a different category, and we said those were alternate interior angles because they're interior because they're on the inside of the parallel lines. They're in this middle area. And they're alternate because they're on either side of the line that's going through, line M, the transversal. So 4 and 6 are alternate interior angles. So it kind of, they're different, and it's going to take a different translation to get there. So, but they are the same. Their measure is equal, so we should be able to use a rigid motion to map those on. Okay, so there's a couple ways to do this. I thought of this way first. If I take angle 4 and trace it out, like so, I'm going to mark a point. I'm going to mark a point here, P. And I'm going to do a rotation of, let's mark P on my overhead as well. So I'm going to do a rotation of 180 degrees around point A. And I know that P prime, the image of P, will be on the line L1 in line with the center of rotation and my original point. Okay, so my angle mapped to angle A. And so now, notice what I can do, not angle A, this point A, angle 2. So now what I can do is I can do a translation along AB. Whoops, marked my paper. I can do this translation here and map angle 4 to angle 6. So let's go back and do that again. And this time I'm going to mark my angle that I'm doing. So here is angle 4 right there. I'm going to do my 180 degree rotation. Okay. Until line P is on line 1 again. So it's 180 degrees. And I mapped angle 4 up here to this other angle, angle 2. And I know I can do that because of the vertical angle thing. And then I'm going to translate angle 4 until angle 4 and angle 6 coincide. And remember, line 1 under a translation is going to map to line 2 because they're parallel. So I used a sequence of translations or sequence of transformations. I can rotate, okay, I can rotate angle 4 around center A, then translate along vector AB. Vector AB. So that's what I did. And then angle 4 maps onto angle 6. Okay. All right, so that's one way you could do it. Another way you could do this is really a lot cooler. You'll need a ruler to do this, to get it exact. What I want to do is mark the midpoint. So this looks like this is exactly, mine is just a hair over 7 centimeters. So I'm going to mark the midpoint of this line. So you can do that on yours. 7.2. So it's going to be about right, 3.6 centimeters. Let's label this M. I hope I got it in the right place. If I do that, something cool happens. And that is that I can do it in one rigid motion instead of 2, which it doesn't matter because we know that a sequence of rigid motions works just as well. But let's use our transparency here. Here is angle 4. I'm going to rotate around this midpoint, and we'll know if I got it exactly right if it maps up. So there's my midpoint, and angle 4 with a single rotation mapped onto angle 6. Okay, admit it, that is cool. Okay, so did you find that transformation? If you did, give yourself a pat on the back. If you didn't, hopefully you can appreciate that it does work. Okay, so let's do, so there's one way we could have done it, or we could rotate angle 4 180 degrees around around center M. And that maps so that then angle 4 would map in one motion onto angle 6. So that's pretty cool. What do we have here? Let's see. I really should have said rotate angle 4 around center A 180 degrees as well. I did a 180 degree rotation up there. Okay, so there's two ways that you could map angle 4 onto angle 6. So part B of that is there another pair of angles with this same relationship? In other words, is there another pair of alternate interior angles? Well, it looks like we've got 4 and 6, and the other pair would be 3 and 5. So I could say angle 3 and 5 and angle 5 have the same relationship. And I could map them the same way. Okay, I want to talk about the last type of angle that we learned about, which is called the alternate exterior angles. So we have angle 2 and angle 8 are, remember, they're on the outside of the parallel lines and they're on the opposite sides of the transversals. We saw those pairs are equal, and also angle 1 and 7 are also alternate exterior angles. So let's look at what happens there. We can rotate those around this midpoint as well. So I'm going to draw, this time let's do this a little more carefully. I'm going to draw this whole line right here. When I rotate this line 180 degrees, it will line up with itself again. So let's mark angle 2. And angle 2, I'm going to say I can map onto angle 8 with a 180 degree rotation around M. So here we go. 180 degrees would take this line all the way to here. And notice that angle 2, which was up here, mapped on to angle 8. And the only reason that that is true is because these are parallel lines. So this segment here that was up here is parallel to, its image is parallel. So it only works here. If we try to use these same arguments on this diagram, again, once again, we did this with the translation, but let's do it with the rotations as well. The reason it doesn't work is because these lines are not parallel. So I could mark this midpoint in here somewhere. It looks like I came close with my point C, but not quite. We'll go in the middle here somewhere. Yeah, I could mark that midpoint M. I could try to rotate around it. This line here, if I draw, for instance, angle 2, and I rotate 180 degrees, let's mark my midpoint so I know what I'm doing here. I'm going to rotate around this point. I can get this to line up, but this, notice this segment here is parallel to L1. And I know that L2 is not parallel to L1, so this is never going to map on. So in this case, angle 2 and angle 8 can only be equal in measure if these two lines are parallel. If they're not, then I don't get that basic rigid motion to map exactly onto the other to the other angle. Okay, so I hope you can appreciate that, and so we can look at our lesson summary now on your homework page or your problem set page, and it kind of summarizes all the notes that we've been taking here. So here's your problem set for lesson 12, and of course I want you to do your exit ticket first, but let's just look over our lesson summary, just to kind of summarize what we've learned. We learned what corresponding angles were, that they are on the same side of the transversal in corresponding positions. So 6 and 8, 1 and 3, and such like that. The example they gave was 2 and 4. When angles are on opposite sides of the transversal and in between the parallel lines, we call those alternate interior angles. So 3 and 7, alternate, and then alternate exterior angles 1 and 5. Okay, so what we've seen is that when parallel lines are cut by a transversal, so L1 and L2, if they're parallel and if they're cut by a transversal, the corresponding angles, the alternate interior angles, and the alternate exterior angles are all equal. In other words, the pairs of them, those pairs of angles will have equal measure. If the lines are not parallel, then the angles are not equal. Okay, and another thing that we could say about this too is kind of the opposite, is I can prove that L1 and L2 are parallel if I know that all these pairs of angles are equal. So if the corresponding angles have equal measure, then I know that these lines are parallel. So it works both ways. If I know the lines are parallel, I can prove the angles are equal. If I know the angles are equal, I can prove the lines are parallel. This will be used, I can't even tell you, over and over and over again in your high school geometry course to do proofs. But by answering these in those exploratory challenges, you were doing informal proofs. So in your problem set, you're going to be asked to do that. In fact, in the exit ticket, you're asked to answer these questions. How do we know that 2 and 6, if these lines are parallel, what do we know about angle 2 and angle 6? Use informal arguments to support your claim. And what they're asking you therefore is, what are the rigid motions that will support your claim that those angles are of equal measure? Okay, so good luck with that problem set, and yeah, have fun. Okay, talk to you later.